In this course, we will study the subjects such as what is simulation, what kind of real-life problems can be solved with simulation technology, and also learn how to program simulation models and run simulation to execute simulation models. Among several simulation types, the discrete event simulation type is the most widely used. It is the discrete event type simulation that we will study in this class. This type of simulation is not about mathematics like statistics or probabilities. It is about logic-based cause-effect procedures. These are the subjects that you will study in this course. First, there is simulation overview. So in this overview, there will be introduction to simulation and how the simulation world is composed, and some classification of simulation model types, and so on. And after that, we first have to learn some theory regarding how to define simulation models. That means how to program simulation models. And that theory is called depth formalism. So once we understand this formalism, we just have to follow the guidelines within this formalism so that the writing programs for the simulation softwares can be easy. And Bayesian model is one of the simulation model types. There are two, and this is one of them, and the other is called coupled models, as shown here. There are two different types of models. Okay. So after learning how to define Bayesian models, we have to learn experimental frame, which is a module needed for running simulation and analyzing the results. That means analyzing results means evaluating the performance of the simulation models after running simulation. So some of the things are not easy to understand at the moment, but don't worry. What I say here will all become quite clear once you have learned that subject. And abstract simulators is another software system needed for executing simulation models. And after learning abstract simulators, we can have in-depth study of coupled models. And there is more subject which belongs to coupled model. Okay, we can separately write down here, or we can make it belong to this subject, but that is called SES, okay, which is a tool for describing the target system or the target problem. 지금 설명했듯이 이것들이 우리가 한 학기 동안 배울 주제들인데 간략하게 이것들이 무엇인가 설명을 했죠. 조금 지금 순간에 이해하기 힘들었던 거는 아마 experimental frame 이하일 텐데 experimental frame은 시뮬레이션을 실행을 하고 나서 성능 평가를 하기 위한 소프트웨어입니다. 그 abstract simulator는 시뮬레이션 모델이 구성이 되면 다시 말하면 시뮬레이션 모델에 대한 프로그램이 끝나고 나면 그것을 실행을 해야 되는데 실행을 하기 위해서는 이런 abstract simulator가 있어야 됩니다. 그리고 커플드 모델은 두 개의 모델 타입 중에 하나입니다. 두 개의 모델 타입은 베이징 모델하고 커플드 모델입니다. 그래서 지금 간략하게 요약한 것들이 무슨 내용인지 정확히 몰라도 돼요. 정확히 안다는 게 이상한 거죠. 그래서 이 주제들을 하나하나 다 공부하고 나면 쉽게 그 내용을 이해할 수 있습니다. Okay, first simulation overview. And among the topics within this simulation overview, let's have introduction first. The most basic question that you have in your mind must be, what is the purpose of simulation or simulation software? In summary, it can be explained as written here. The simulation softwares replicate and predict the behavior, or the behavior can be described as activities or events of real systems and that currently exist or are expected to exist in the future. So replicate means it copies the behavior or predicts the behavior of the real system. Okay, so this is the target system or target problem that we want to solve the problems. So either it is called as target system or the problems or target real systems. Okay? All these words can be interchangeably used. That currently exist. That means there is this system existing in the real world at the moment. Okay? Currently exist. Or this can be the target system that we want to solve the problems. Can be some future system, something that are expected to exist in the future. So if it is future system, what is this about? Okay. If it's some future system, it is something we are currently designing the system. Okay. In designing the system, there are two aspects that we have to consider. No matter what that system is, it can be some building, it can be some factory, or it can be some network. It can be anything that you can think of. First, we have to structure. And another structure, and the other is, as written there, behavior. We can design the structure of the target system in many different ways. Okay? This is about the layout, usually represented by blueprints if it is building. 건물이면 청사진이라는 게 있죠. 청사진은 건물의 구조도를 나타내죠. So in designing, we have to include structural design and behavioral design. But the behavioral design cannot be done with blueprint. How this can be designed? This can be designed with simulation models. Because what we are doing with simulation models is that we are building, if there is a real world, this is real world, and the real world target system is copied by the software. This is software and this is target system. Let's call this problem at hand. Problems are described by software, and the software exists where? Cyber world. Cyber world, not real world. Okay. So we want to build the target real system, which is problem, into the cyber world with the software. So if the problem is about building complex, the building architecture or traffic system, then we are writing simulation models that correspond to those, either tall building or traffic system. We actually build here, build buildings here, or we build traffic system here, city traffic systems. By this time, software called simulation model. So once these are built, then we can execute and let the car pass by, drive through this road, or let the simulation software make use of this building, operate this building, and see how this works. Okay. By looking at the operations within these systems, we can analyze whether we are correctly designing or not, designing the buildings or designing the traffic systems or not. Okay. So in this way, with the simulation software, we can design behavior of the target system. So the purpose of simulation is, in short, to replicate the behavior of existing system or predict the behavior of future system. And in order to have this behavioral design or behavioral analysis and prediction, there should be a different way to write programs for the simulation models. So what is the major difference compared to conventional software? The conventional software means most of the existing software. Okay. I better say all the programs that you have written or you have programmed so far, you took courses like data structures, algorithms, and other courses. And you did a lot of programmings, but all those can be classified as conventional software, unless you have done some simulation programming. So other than simulation programs, all the programs belong to this conventional software. But that is how we distinguish in this class or in the field of simulation. So what is the major difference? The difference is described here. In simulation software, both time and space values are used to correctly describe and solve the problems occurring in the real world. And the problems is what? The target system or the real system. So we need both time and space values, which also means that in conventional software, only space values were used in writing programs and solving problems with that software you have written. When you write the programs that makes use of certain algorithms like graph algorithms, okay, you used variables. And the variable, when you, after defining variables, you have to assign values. Think of the values that you have assigned to those variables. Those are all space values. Within the variable, you have assigned space values. Either this is some mathematical values or symbolic values. For example, 2.3 or just 78. So these are numeric values, and either some numeric values or symbols like left, right. Somehow you represented these symbolic values within the variable. But in this simulation software, both the variables should have both time and space values, not just left, right, and numbers. We also have to keep track of when certain values occurred or when certain values should change or change, things like that. So time is important. Okay, why do we have to make use of these two different values? Think of this, the real world. This is the real world that we live in. Within this real world, there are many activities or events occurring in this real world, and those are under the influence of time and space. Both time and space values are required to describe the problem or describe the target system and solve the problems with it. Without time, nothing can be correctly described in our real world. For example, think of what you're going to do in a single day. It's like a daily schedule. You wake up, you wash your face, and probably have breakfast, and wear some proper clothes, and heading to the university, go to the university, and take classes, and so on. These are the orders, but in order to be a meaningful schedule or itinerary, you have to have time. Wake up at what time? And leave home for school by what time? And your first class starts at what time and it ends when? And when second class starts, and so on. So in order to have meaningful schedule, there must be time plus space values. Time is about when, and space value is what to do. Okay. So it's getting congested, but let me try to write down here. This is about when, and this is about what. It means what to do. If you take this time out, then it is meaningless, just orders, okay, which not describe the problem of daily schedule correctly. This is your target, daily schedule, and solving problems related to the schedule. That means the things that are described within this schedule. In order to perform according to the schedule, you need both information. When, what to do. This is the reason why to correctly describe the problem, we have to make use of both time and space values. This is reason behind why simulation software, this is also called a simulation model, is based on time value and space value, as briefly explained here. That is the biggest distinction between conventional software and simulation software. 다시 한번 간략히 정리를 해보면, 제일 궁금한 게 시뮬레이션의 목적이 뭐냐죠. 시뮬레이션의 목적은 타겟 시스템은 대상 문제죠. 그래서 대상 문제가 뭐 어떤 큰 빌딩에 관한 것일 수도 있고, 또 컴퓨터 네트워크에 관한 걸 수도 있고, 스케줄링에 관한 것 수도 있고, 아니면 도시의 교통 시스템일 수도 있고, 굉장히 대상은 많습니다. 이런 리얼 시스템, 실세계 시스템, 이런 실세계 시스템의 행동을 replicate, 복제하고 재현해내고 그 다음에 예측하는 겁니다. 그래서 이제 복제를 해낸다는 것은 currently existing, 현재에 대한 시스템이고, 예측을 한다 하는 것은 미래의 시스템이 되겠죠. 그래서 현재 시스템에 대해서 복제를 할 수 있으면 그거를 이제 다각도로 분석을 할 수가 있습니다. 이렇게 실행을 해보고 저런 상황에서 실행을 해보고 그래서 개선을 할 수가 있죠. 변경을 할 수도 있고 구조를 아니면 또 기능을 변경을 할 수도 있고 미래에 대한 건 아까 얘기했지만 이제 설계를 하는데 설계에는 두 가지가 필요하다 그랬죠. 구조적 설계하고 행동에 대한 설계, 동적인 설계, 정적인 설계를 말하는 거예요. 그래서 만약에 건물이다 그러면 구조적 설계는 뭐 청사진이라 그러죠. 블루프린트 같은데 할 수 있는데 동적인 설계는 할 수가 없어요. 그거는 그 자체가 정적인 정보이기 때문에. 그래서 동적인 설계는 실제로 제일 이제 확실한 건 실제로 건물 같으면 지어놓고 또 도로 같으면 건설을 해놓고 사용해 보면은 금방 알 수가 있죠. 뭐가 잘못됐냐. 변경을 하면 돼요. 개선을 하면. 근데 이제 그 고치는 게 쉬운 일이 아니죠. 비용도 만만치 않고 시간도 오래 걸리고 또 그 사이에 불편도 많았을 거고 설계를 정확하게 하는 게 중요하죠. 그래서 그 대상 시스템, 실세계 시스템 이거를 이제 대상 문제라고도 얘기한다 그랬죠. 그래서 앞으로 이 과목에서 계속 뭐 타겟 시스템 또는 프로블럼 이게 다 똑같은 말입니다. 그거를 실제 사이버 월드에 프로그램으로 만들어 보는 겁니다. 소프트웨어로. 그래서 이 시뮬레이션 모델이죠. 건물도 지어보고 사이버 세상에 또는 도로도 건설해보고 그래서 여기서 다 실행을 해보고 가장 적합한 구조를 설계를 하는 겁니다. 구조와 기능을 말하는 거죠. 그리고 이제 가장 큰 특징이 뭐냐? 시뮬레이션 소프트웨어의 시뮬레이션 모델의 가장 큰 특징은 시간하고 공간 값을 다 사용한다는 겁니다. 두 가지가 다 있어야 돼요. 안 그러면 정의가 안 됩니다. 그래서 왜 그러냐 하면은 대상 문제를 정확하게 표현을 하고 해결을 하려고 합니다. describe and solve 그죠? 항상 문제를 해결하려면 먼저 정확하게 표현을 해야 돼요. 그리고 그 표현된 방법에 의해서 해결을 하는 겁니다. 그래서 표현을 하고 해결을 하는 겁니다. 어떤 것에 대해서 실세계에서 일어나는 문제들에 대해서. 그래서 왜 시간하고 공간값이 다 필요하냐 하는 거는 아까 설명을 했었죠. 다시 반복하면 가장 근본적인 이유는 우리 실세계가 시공간 세계라 그랬습니다. 그렇습니다. 시공간 세계에서 어떤 일이 일어난다. 그럼 당연히 시간하고 공간 값에 의해서 정의가 되겠죠. 그래서 시간하고 공간 값으로 표현을 하고 그것을 사용해서 풀어야 돼요. 그래서 정확하게 할 수가 있죠. 만약에 옛날 일반적인 프로그래밍 방법처럼 공간값만을 사용한다면 그리고 하루의 스케줄을 생각을 해보죠. 데일리 스케줄을. 아침에 몇 시에 스케줄은 일반적으로 어떻게 구성이 되어 있느냐 하면 일반적인 실생활에서의 스케줄 먼저 얘기를 해보죠. 어떻게 구성이 되어 있느냐 하면 아침에 몇 시에 일어나서 언제 밥 먹고 옷 입고 언제까지 집을 떠나고 학교에 몇 시까지 도착해서 첫 시간은 언제 하고 또 그게 언제 끝나고 둘째 시간은 언제 시작하고 그래서 보면 스케줄이라는 문제가 구성이 되려면 표현이 되려면 언제 그 시간값이죠. 그다음에 무엇을 공간값입니다. 두 가지 다 있어야 돼요. 안 그러면 의미가 없습니다. 그냥 시간값이 없이 공간값만 있다 그러면 그냥 일어난다, 아침 먹는다, 학교 간다. 뭐 시간 제약이 없으면 말이 안 되죠. 아침에 오후 3시에 아침이 아니라 일어나는 시간은 뭐 아침이라 그러죠. 오전 8시다 또는 7시다. 그 다음에 집은 시간 정보가 없으면 오후 3시에 떠난다. 그리고 첫 교시는 저녁 8시에 듣는다. 첫 시간은 10시간 동안 지속되다 끝난다. 그럴 수도 있는 거죠. 틀린 게 아니죠. 왜냐하면 시간 정보가 없기 때문에. 그렇지만 말도 안 되는 스케줄이죠. 그래서 이렇게 시간값이 중요합니다. 그러니까 실생활에서는 시간이란 값을 안 쓰면 별로 풀 수 있는 문제가 없어요. 왜냐하면 표현이 정확하게 되지 않기 때문에. 그래서 시간하고 공간값이 다 사용이 돼서 문제를 표현하고 그 문제를 프로그램해서 풀어야 된다 하는 것은 너무 상식적인 얘기입니다. Okay? Then you may wonder why we are not doing in this way from the beginning. There is reason. There are two different reasons. First, it takes too much time. That means too much time of computation is required. Computer computation time may be too low, too slow. And another, because of this, we didn't have good theory. So the theory has been developed. I mean, sound and reliable theory has been defined about several decades ago. But even then, we didn't have enough computing power. These days, we have better machines, better computer systems, so that it is good time to tackle the problems with simulation software technology. If you look at the program codes later on simulation software, it is not much different from conventional software in which only time values are used. There is not much of difference. The only difference is it introduces or includes the time values systematically under some sound theory. That's all. The simulation software looks exactly the same. The only difference is the time value usage or inclusion of the time value. So I hope this can be some easy introduction to simulation course, and we will look at some specific subjects from now on. This figure shows how the computer simulation is composed. That means what are the components within computer simulation system. There are three components. This is the target system. Also, this can be described as real or proposed system. The real system means the system that currently existing, and proposed system is the future system that is under design now, something to be built. And there is model. This is simulation model. So this is some program. And there is another component called simulator. This is also software that executes the instructions or programs within this model. So we need these three components. It's simply the target system and simulation program and the other program that executes this program. So this real or proposed system becomes source of data. By looking at the information and specification and any other information within the target system, we are writing a program to build simulation model, and this activity is called modeling. So modeling and simulation are two different activities. As a result of modeling, we have a program which is set of instructions. Or, as I said, this is program, software. And this program, as described in the introduction, makes use of both time and plus space values. So this time usage is the distinct difference compared to the conventional software. And once we have this simulation software, we can execute and see how the target system behaves. And this activity is called simulation. And this is being done by simulator software. Later in this course, we will also learn how this simulator is composed. What are the components within this simulator and how each component works and how those components cooperate in order to run simulation. Okay. So here is the main idea behind this diagram. Once we have constructed this simulation model, it should be executed. It means execution of model should be done. And after executing the models, what do we get? The behavior. That means execution of model generates behavior of the, of course, simulation model, but since model represents what describes the target system, this behavior is what? Behavior of, this is actually behavior of this system, the target system. So after obtaining this knowledge regarding the behavior of the target system, then based on that, we can make certain decisions. In order to make certain intelligent decision is the main purpose of building simulation models. Okay. The immediate purpose of computer simulation is to build simulation models that replicate and predict the behavior. But once we obtain the behavior, ultimately it is used to make certain decisions. And depending on the validity of this knowledge, the behavioral knowledge, we can make decision 100% dependent on this knowledge, behavioral knowledge. So it can be 100% dependent on this result, or it can be as low as 20 to 30%. Okay. Usually somewhere in between. Can be 20%, 30%, or 40%, or 100%. For example, we have built a simulation model for economic flow, predict future economy based on simulation models that somebody has built, and run simulation and get the result. Can we be 100% dependent on that result? Probably no. If we can predict the future economic trend accurately so that we can rely on result 100%, then probably everybody in this world can be super rich. Right? But that doesn't seem to be realistic, right? Because building simulation model for the economic trend prediction is very hard because there are so many factors affecting the future economy. So even if with current technology, no matter how accurately we build the simulation model, we should rely on something near, in the worst case, about 20 to 30%, probably for the best, above 50%. But I'm pretty sure it cannot be close to 100%. In between these two extreme values. These two extreme values. And some other target system behavioral result can be utilized with the level of, at the level, we can say 80%. That means we can rely on the result about with 80% confidence. And this can be described in this way. The validity. This is proper terminology. The validity of the model or the model's result is, for example, 80%. And so that for this percentage, we can rely on the result. There are many different ways to describe how much we are dependent in making decisions. You can use the word rely on, or it is that much valid, and we can utilize the result to that percentage. Okay, and this is interesting case. Then when are we able to rely on the result 100%? This is usually for real-time intelligent control. So 100% case is usually for real-time control. So in order to have real-time control, it should be intelligent. 똑똑해야죠. Should be intelligent. So this intelligent controller is composed of simulation models, programs. Within this program, there are logics which determine the proper control of the target system. If it is about traffic system, and say there is a traffic light, and this must be controlled properly. So should assign proper time for green light and proper time or duration for red light and yellow light, and some traffic light has arrow, so left turn, and so on. So we can build intelligent controller for this with simulation model. So in this case, after this traffic light controller runs fast simulation and determine the best duration of these values. In this case, if simulation model generates certain behavior, that means certain simulation result, then this traffic light or controller has to accept the result 100%. Okay, the validity is 100% in this case, because the human cannot intervene in this case. So this is the system where the simulation result is employed 100%. And I also have explained some case where we cannot rely on 100%. 다시 정리하면 시뮬레이션이 형성되기 위해서는 이 세 가지 요소들이 있어야죠. 첫 번째는 또 타겟 시스템에 관한 거죠. 그래서 그게 이제 현재 존재하는 거일 수도 있고 아니면 미래의 시스템, proposed 시스템일 수도 있습니다. 그래서 이게 데이터 소스가 돼서 여기 있는 정보들을 이용을 해서 또는 보고 모델을 디자인해서 프로그래밍 합니다. 그것이 모델링 액션이죠. 그래서 모델이 구성이 되면, 즉 시뮬레이션 프로그램이 구성이 되면 그걸 이제 실행을 해야 되는데, 실행은 시뮬레이터라는 소프트웨어가 하죠. 그리고 실행을 하고 실행한 결과는 어떤 behavior를 제너레이션 하는 거죠. 만들어내는 겁니다. 다시 말해서 동적인 지식을 만들어내는 거예요. 그러면 이 결과로 시뮬레이션 결과로 나온 동적 지식을 얼만큼 활용을 하느냐, 의사결정을 하는데 얼만큼 활용하는가. 보통 최저는 한 20%, 최고는 한 100% 정도로 보면 적당합니다. 그래서 만약에 미래의 경제 그림에 대한 시뮬레이션 모델을 만들었다. 그래서 시뮬레이션 해보고 그 결과에 따라서 투자라든지 기업에서 의사결정을 하면 되는데 그게 100% 정확하다 하는 것은 비현실적이겠죠. 너무 복잡해서. 그래서 최악의 경우는 한 20% 정도는 돼야 그래도 실효성이 있을 거고, 그리고 100하고 20% 사이겠죠. 그래서 얼만큼 100에 가까우냐 하는 거는 얼마 많은 시간과 비용과 노력이 투자됐느냐, 시뮬레이션 모델을 만드는데 달린 거고, 어쨌든 쉽게 100은 아니겠죠. 그런데 어떤 경우에는 이제 100인 경우도 있어요. 왜냐하면 실시간 컨트롤러가 있다. 예를 들면 실세계에서 자동차들이 이렇게 오가는 길이 있는데 거기에는 신호등이 있죠. 신호등을 시뮬레이션 모델로 실시간 시뮬레이션 모델을 만들어서 할 수가 있는데 이런 경우는 여기서 준 결과를 100% 수용을 해야 됩니다. 그래서 대개 시뮬레이션을 하고 나서 그 결과를 의사결정에 사용을 하는데 사람이 사용하는 경우도 있고 아니면 어떤 시스템이 컴퓨터 시스템이 사용하는 경우도 있죠. 그래서 보통 이제 사람이 없는 경우는 100%에 가깝고 결과를 사람이 보고 하는 경우는 20%에서 100% 사이가 되겠죠. Let's think of where the simulation models can be applied, application domains. And this can be applied to most of the artificial systems. Artificial systems, that means man-made systems. What is the characteristic of an artificial system? Generally, these artificial systems are complicated, and the activities within this artificial system cannot be expressed numerically. That means we cannot describe or express the problems in artificial systems with mathematics. So this is where we can apply simulation technology. If the problems can be expressed by mathematics and solve the problems by solving this mathematical formula, that is best. But most of the artificial systems that mathematics cannot be applied in solving the problems. The reason is it is very hard to express the problems or the activities within the system. Okay. Think of a certain manufacturing factory. Okay, there is a factory, and think of the activities occurring within the factory. Can you describe most of the activities within the factory by mathematics? It is impossible. For example, there is some person working with certain device, and say that he is painting on this table, or he is assembling on this table, or he is cutting within this table. Okay, these activities are not easy to be described by mathematics. And in the middle of his work, he may want to go to bathroom. Okay? And on his way to bathroom, he may fall down. And he may continue to walk, or he may not recover from this fall down. Or in the middle, he suddenly becomes hungry and wants to take some meals. And in front of some cafeteria, he orders something. Okay, all these activities, expressing this with mathematics is very complicated and most of the time impossible. But with simulation models, we can describe these activities. Okay. So that's the reason why the simulation technology can be applied to artificial systems for solving problems. But not only to artificial systems, it can also be natural systems. like studying ecological systems or geological systems or something related to cosmos. That means the objects within the space can also be studied. For example, what are the artificial systems like network, computer network, or it can also be human network. And the world system. In fact, world simulation is one of the popular areas for applying the simulation technology. So the country like US performs a lot of simulation before any engagement or any initiation of the war. So do a lot of simulation and develop a lot of tactics or strategies and choose the best strategy possible and apply in real battle. In this way, the percentage of winning the battle can be maximized. So this is very popular area for application. And the simulation model can be applied to traffic system. Many traffics. A traffic system formed by airplanes or trains or ships or automobiles. And there can be other different types. And airport, building airport. Airport is one such complex system. So building airport requires building simulation model, definitely. And many manufacturing systems. There are many different manufacturing systems. Some semiconductor manufacturing system is very complex because it takes several months to produce output once the materials are provided to this manufacturing system. That means it takes several months to have the result once the input is provided. So that must mean that the process is quite complicated. There are many different steps within this system because it takes several months to have the result. So in building this manufacturing system, if we can design the structure and functionality of this factory, can be very helpful. And space station seems like this is more complex than manufacturing system or airport. Think of there is Mars, and we want to build some space station. Then this should have many functionalities, and the structure must be quite complex. So this is good area for running simulation. And all these systems can be also classified in view of these aspects. First, we can apply the simulation models to existing system. For what? If it is applied to the existing system, then it is for analysis of current performance or analysis of current strategy or the current schedule. And after analysis, we can modify to improve the performance, modify structure or modify the strategy. It can be physical or it can be just something related to mental. We can modify in terms of these two aspects. And we can extend the existing system to accommodate new demands or test alternative strategies. This is related to mental changes, mental improvement without physically changing or extending the existing system. And also we can apply to future systems, as I explained. And when we apply, it is for dynamic designs. Including dynamic designs means the structural design is also included. In order to have dynamics, the structure is must. Actually, this is quite interesting concept in why we need structure. The end purpose for having structure is to generate certain behavior. So when we say dynamics or behavior, then by default, the structure is included. 항상 스트럭처의 목적은 특정 다이내믹스나 비헤이비어를 만들어내기 위한 겁니다. 항상 우리의 최종 목적은 행동에 있어요. 비헤이비어나 다이내믹에 있습니다. And the simulation models can be applied in building intelligent systems, not for replication and prediction. Other than replication and prediction, we can control the system with simulation models, and we can use simulation models for planning and what to do in the future. It's planning, and the planning also includes scheduling, when and what to do, and monitoring. Monitor the operation of current system, whether it is operating correctly or not. If there is something wrong with current operation, then detect that and provide corrective action. That means fix the operation.